Hi, good morning everybody. So, we were discussing fast reactions, that is techniques for fast reactions. So far we have talked about reaction rates, rate laws, effect of temperature on reaction rates, then complex reaction, theories of reaction rates, kinetics of some specific reactions, kinetics of catalyzed reaction. Now we are here with fast reactions. Now we discussed techniques like flow techniques, that is continuous flow method or maybe stopped flow method. So these are the typical diagrams of flow methods. I mean, there are two syringes, there is a mixing chamber and then there is a detector, and this detector may be movable, or maybe these syringes can also be movable. Okay. So with this we can study fast or moderately fast reactions, not very fast reactions. It is not possible to follow the kinetics of those very fast reactions with this simple flow technique. So for that a modified version of flow method, that is your stopped flow. Okay. So here also there are two syringes, there is a mixing chamber and you have got the detector. Okay. So you have got the detector, that is which detects the spectrophotometrically or maybe fluorometrically, and there is a stopping piston and there is a switch. There is an electrical switch. The moment this stopping piston this part is this electrical connection is completed, then source is illuminated and the detector detects the signal. Okay. So and in this case this stopped flow technique, this does not require too much of volume, but here maybe it requires a moderately larger volume of reactants. So in this way it is smarter than this one. Then you discussed this relaxation techniques, shock wave method, and lastly we talked about this flash photolysis. Talked about means we just given an idea of this flash photolysis. Now when the term flash photolysis comes, then automatically this laser flash photolysis comes into our mind. Now before that, let us have idea of this flash photolysis. Okay. What is this flash photolysis? Now suppose we have got a sample containing active species. Okay. Now the idea is that you have to shine with short pulse of light. Maybe it's like flashlight, or maybe laser light as well. I will come to lasers later on. So this is an active material. So suppose you have got the molecule M. When it is allowed to interact with radiation H nu, maybe it goes to some electronically excited state, and then it undergoes further reaction. Reaction, maybe it is photophysical, maybe some M and maybe heat, or maybe photon, or maybe some chemical reaction. Okay. So chemical reaction is also possible. So in this case the active ingredient for the reaction is active material, or the reactant is this one. So by some means, and this is also not like a ground state molecule that it stays for long time. It is not like that. Okay. it is not like that this M star stays for a long time. So, eventually it will undergo these processes. So, therefore, with time this population of this M star reduces. Okay. And suppose if it is the case like say this one absorbs at say lambda 1 and say this one absorbs at lambda 2. Okay. So, the excited species, if it is absorbing at a different wavelength, then with the help of spectrophotometry we can monitor the concentration of M star as a function of time. Okay. So, that means this flashlight is used to generate this active species, and there will be another light which is called the probe light. Okay. So, which measures the absorbance of this species and maybe as a function of time. So, what you do, you have got your sample over here, maybe it is an aqueous solution or maybe solution in some solvent, maybe methanol, maybe benzene or so on. Okay. So, you have got your flashlight over here, flashlight, and this side you have got your probe beam. It is a weak maybe white light, okay, and you have got the detector. You have got the detector. The thing is that the moment this flashlight is on or it is flashing, electronically this detector becomes on. I mean, getting a pulse from this flashlight, a circuit is turned on so that the detector becomes active and it starts to detect the signal at a given wavelength lambda 2, okay, and as a function of time. So, this detector is plugged, I mean the signal from the detector is plugged into a device, maybe it is a oscilloscope, cathode ray oscilloscope or maybe oscilloscope. Nowadays these oscilloscopes are replaced with PC based oscilloscopes. So, what it does is it records the signal intensity as a function of time. So, the signal strength decays with time. Okay. So, it is the intensity, okay, intensity or maybe absorbance, ABS, and it is time. Okay. So, what happens is that the probe light, because of this absorption at immediately after this flash is on, what happens that this when the flash is on, this signal is minimum because immediately after the flash is on, this population is very high. So, therefore, what happens if you just simply record the intensity of the emergent probe light at a given wavelength lambda 2, you will have a rising trend of your intensity, because this species, absorbing species, is decaying with time. Okay. So, this way we can follow the concentration of M star. Now, sometime this active, I mean this sample does not have strong absorbance at a particular wavelength. Okay, it may have weak absorbance. So, in that case, if you can have a very high intensity light, then it is possible to have a significant absorption at that particular wavelength, and for that this fluorescence light is replaced with lasers. Okay. So, now we will come to what is meant by lasers. Okay. So, it is the short form of the term light amplification by stimulated emission of radiation, LASER. So, what is this light amplification? What is this stimulated emission? So, we will come to this. So, let us have a look into into a typical simple laser. Say it is a helium neon laser. It is a visible laser. I mean, lasing frequency is visible, and lasing frequency is visible. So, and this picture is taken from some internet resource. Now, this is a helium neon laser. It has got like there is an active medium. This is the power supply. Okay, this is cathode, this is anode, and it contains mixture of helium and neon. And this mirror is 100% reflecting. This mirror is 95% reflecting. Now, because of this electrical discharge, lasing action is generated. Now, see, this one is not 100% reflecting. So, it is giving, this side is giving lasing, I mean laser light, the whatever we get from this box. Okay, and this side is 100% reflective. Okay. Now, what is this laser action? That suppose you have got like two level system. Okay. Now, in two level system, because of this Boltzmann distribution, the lower level is always populated higher than the upper level, and since this gap is electronic gap, so always this one is having very high population, that is most of the population is over here than here. So, therefore, ordinarily you cannot have population over here more than over here. Okay. Now, suppose if you have and if you have a population, I mean like this level, I mean upper level higher than the lower level, then there is a possibility of lasing action. Okay. So, what is happening, that suppose we have got a third level, ordinarily this level is not populated. Okay. If this level is not populated, and suppose if you excite, I mean if you pump the system with brief pulse of radiation, then what is happening, that this excited species will rapidly move to this level, so that if this is a metastable state, that its population remains finite for some time, then at ordinary situation this one is never populated, but because of this roundabout channel, this level gets populated. Okay. So, what is happening, that eventually this level will have a finite population. So, compared to normal population, this level is, I mean normal means under ordinary condition this is 0, population is 0, but because of this optical pumping this level gets some population. So, it is called the inversion of population with respect to when there is no pumping. And then this excited, I mean this population, and some of the excited species, okay, gets de-excited, I mean because of your spontaneous emissive tendency, some of them will come down, okay, giving rise to photon. Okay. What is happening, that if you can feed this photon back to here, then it will stimulate another system to come back. So, it is a cascading action, and therefore, all the population will all on a sudden come down, giving rise to a huge number of photons, okay, and which is called basically lasing. Okay. And this lasing, it has got specific characteristics, so which we will come to one by one. Now, lasers, it is, and one more important point, that it is a 3-level lasing case I discussed. We may have a 4-level case also, like here. 3-level case, it is these 2 levels are never populated under ordinary condition, but if you do pumping like this, you will have population, finite population over here compared to this one. So, it is again against the normal case, that is Boltzmann distribution. So, population is getting inverted, therefore, we can expect lasing between these two levels. Okay. So, let us come to the characteristics. So, light emitted from a laser is monochromatic, that is, it is of one color and wavelength. In contrast, ordinary white light or maybe yellow light may be a combination of a band, a band of frequencies. It is not a single frequency. Okay, but for lasers it is a monochromatic, that is one frequency is there. Why it is that? Because lasing occurs between two definite levels, that is a pair of levels, these two are definitive. Therefore, the gap between these two levels is fixed. Therefore, we can expect only one frequency. Okay. And lasers emit light that is highly directional. Why highly directional? Because as I told you that because of this spontaneous emission, this one as I told you earlier, that because of this spontaneous emissive probability, this comes down to here giving rise to a photon, and if you can have this photon within a pair of mirrors, then what will happen? Suppose in between these two mirrors there is an active medium like this. So, this is the active medium. Okay. So, this active medium means that is it has got the excited ensemble. Okay. So, excited ensemble means this ensemble, this one. Therefore, the moment this single photon is emitted due to spontaneous emission tendency, this may fall onto maybe this mirror or maybe the other mirror, and if this spontaneously emitted photon falls onto this mirror vertically, okay, vertically this way, then it will be reflected back and pass through this active medium. Okay. So, pass through this active medium means it will go back and forth between these two mirrors and giving rise to a standing wave pattern. So, a standing wave pattern will be generated, and the more it will go like this, it will stimulate other excited other excited molecules or excited systems to come down. Okay. And there is a kind of avalanche breakdown, like all the the excited ensemble will together come down to the ground state, giving rise to photon, and only those photons which are exactly or very close to the vertical situation compared to this mirror will remain within the cavity, which is this region in between these two mirrors, and the active medium is called the cavity. So, it will remain within the cavity. Okay. So, within the cavity means those beams, those rays which are exactly vertical to this mirror will oscillate within the cavity. And as I told you in the earlier diagram that one mirror is 100% reflecting and the other mirror is less than 100% reflecting, means some of these oscillating photons, waves, some of these oscillating photons within the cavity will exit the cavity through this less than 100% reflecting mirror. Okay. Therefore, whatever light we are getting as a lasing should be exactly very directional, because it comes out of these two parallel mirrors. These two mirrors have to be very specific, like they have to be parallel to each other. Okay. Therefore, it is highly directional, and laser light is emitted as a relatively narrow beam in a specific direction. Ordinary light, which ordinary such as bulb light, is emitted in many directions, all the possible directions, but lasing is a very directional thing. The light from a laser is said to be coherent, which means that wavelengths of the laser light are in phase in space and time. Ordinary light can be a mixture of many wavelengths, because as I told you, the standing wave pattern is generated, means when this standing pattern remains there, the situation is that if they oscillate in phase, if they do not oscillate, these waves do not oscillate in phase, then there will be destructive interference. Therefore, those waves which will survive within the cavity to form the standing wave pattern, these should maintain a constant phase difference, or they should oscillate in phase. That means whatever waves are there within the cavity forming the standing wave pattern, okay, will be in phase. That is why the laser light which is coming out of the cavity is coherent, that is, a constant phase difference is maintained, or maybe they will oscillate in phase, I mean like this. Same way, if means for say this one is one wave, this is another wave, so they have to oscillate in this way, or maybe there will be a constant phase difference maintained. It is never like one is going this way, other is going that way. So, in that case the destructive interference will stop everything. So, therefore, this makes laser light, coherent. Okay. So, it is a comparison between bulb, ordinary bulb and laser. So, it has many wavelengths. The laser will have broadly one wavelength. There is monochromatic, okay. But monochromaticity does not necessarily mean that only one wavelength. It also depends on the time scale. So, that part I am not going to discuss anyway. And for incandescent, it is a multi-directional, okay. But for lasers, it is directional because it comes out of two parallel mirrors. So, therefore, it is highly directional, and also I told you that it is coherent. Why coherent? Because of this standing wave pattern is the requirement, because if standing wave pattern is not there, then those photons will leave the cavity, and when the photons photons from this spontaneous emission of this excited ensemble is leaving the cavity, they are no longer able to stimulate the excited ensemble to come down, giving rise to photon. Okay. So, that is why coherence is coming, but for incandescent, that is ordinary light, it is incoherent. Okay. So, this is this is all about incandescent, and with respect to properties. So, let us come to components of lasers. Active medium, first one is called the active medium. Like, let us go back to this picture. This is the active medium, okay. It may be like helium neon, as I have shown over there, helium mixture of helium neon. It may be ruby, okay. It may be neodymium, yttrium, aluminium, garnet crystal, maybe liquid dye, or gases like carbon dioxide, or like helium neon, or maybe semiconductor like gallium arsenide. An active media, that contains atoms whose electrons may be excited to metastable energy level, as I told you, by an energy source. So, metastable state is generated by means of maybe electrical pumping or maybe optical pumping. Electrical pumping is also possible, optical pumping as I have discussed with 2-level system or maybe 3-level system. So, for your helium neon case, it is electrical pumping. Excitation mechanism, it is called the pumping process, like pumping water from from the ground level to the top level, okay. So, pump energy, so excitation mechanism pumps energy to the active medium, okay. Like optical method, maybe electrical method, or maybe a biochemical method, okay. So, there must be a way to pump energy from here to here, okay, by this route. Okay. Then high reflectance mirror. High reflectance mirror means if you have a lasing cavity, you have got this active medium, you have got this mirror, there is another mirror. So, one mirror will have to be 100%. Okay. You have pumping, okay, pump energy, it may be optical, it may be electrical and so on. Okay, so, this is 100% reflecting mirror, and these two mirrors need to be parallel, very parallel. Okay. If one of them, I mean if they fail to become parallel, then you will not be having lazy. And there is another mirror, or maybe it is called the partially transmitting mirror. Okay. So, it will be less than 100% reflecting, maybe say 95 to 99.9%. Okay. So, what happens that this reflects all the photons which are falling onto this mirror, but this reflects maybe 95%. I mean suppose 100 photons are falling on this mirror. So, what is happening that out of 100, 95 photons are fed back, I mean returned to this cavity, and maybe 5%, I mean 5 photons are coming out, which you see as lasing. Okay. So, and since this light is coming because of these two parallel, I mean out of these two parallel mirror configuration, so these being photons will be exactly parallel. Their divergence is less than 1 radian, or even very less than 1 radian. So, very low degree of divergence. Okay. Contrary to our, or I mean ordinary lamp case, where light is emitted in all the possible directions and intensity falls off rapidly with distance from the source, but here it does not fall that it does not fall that much, okay, with separation. I mean if the intensity over here is having some value, maybe here also that value is very close to this value. Okay. So, active medium, this one is your active medium. Excitation mechanism, pumping energy, okay, pumping energy from maybe here to here and then lasing. Okay. High reflectance mirror and partially reflecting or maybe partially transmissive mirror. So, these are the basic parts of a laser. So, it is a typical gas laser description. This one is a rear reflector. This is actually called output coupler, OC. Output coupler means it is partially transmissive mirror, and gas discharge. Through gas discharge, your excited ensemble of molecules are created, and then through this rear reflector, 100% reflector and output coupler, the beam is coming out. Okay. So, gas lasers consist of a gas filled tube placed in the laser cavity. So, like it is the active medium. A voltage, the external pump source is applied to the tube to excite atoms in the gas to a population inversion. Population inversion is a must. Okay. And light emitted from this type of laser is normally continuous wave. Continuous wave means it is not like a flashlight, it continuously remains, I mean its intensity remains constant with time. It is called the continuous wave case. Okay, generally these gas lasers will give rise to CW mode, continuous wave mode. Okay. So, lasing action, let us say in points. Energy is applied to a medium raising electrons or maybe molecules to an unstable energy level. Okay. So, like here, say this one is unstable energy level, this is your unstable energy level. Okay. Then maybe it is because of this electronic excitation it happened, or maybe some other means, maybe collision could be another way of pumping. I mean collision, by collision you can, I mean because of energy exchange, excited ensemble can be created. These, and then what happens, these atoms or excited ensemble spontaneously decay to a relatively long-lived low energy, this is your metastable level. Okay. A population inversion is achieved when majority of atoms have reached, you know, majority of atoms have reached this metastable state. Okay. And then, so majority of atoms when made this this transition, then there is a sufficient population built up. Okay. Then lasing action occurs when an electron or maybe an excited ensemble spontaneously returns to the ground state and produces a photon. Okay. Maybe because of the electron de-excitation from here to ground state, or maybe a molecule comes back. This is called that molecule comes back to the ground state, maybe electronic transition or maybe by some other transition, vibrational or maybe some other transition. So, it comes back and giving rise to a photon in the appropriate frequency. Okay. If the energy of this photon is of the precise wavelength, it will stimulate the production of another photon of the same wavelength and resulting in a cascade effect. That is, if this energy of this emitted photon is exactly matching with this energy gap between these two lasing level, then what will happen, that it will stimulate another excited molecule to come back, resulting in another photon. So, one photon makes another photon, then these two photons will make 4 photons. So, this way a cascading effect happens. Okay. The highly reflective mirror partially reflect, I mean highly reflective mirror and partially reflective mirror, you know, continues the reaction by directing photons back through the medium along the long axis of the laser. Okay. So, as I told you that these photons are fed back into this active medium, okay, and only those photons which are falling onto the mirror exactly perpendicularly will remain through back and forth, you know back and forth reflection, and will make standing wave pattern. Then the partially reflective mirror allows transmission of a small amount of coherent radiation that you observe as beam. Okay. So, because of this partially reflecting mirror, a little percentage is coming out, what you see as lasing. You see, if 100% could have been directed outside, then we could have got huge intensity, but in that case we will lose the cavity. So, that is why keeping the cavity on, we have to have most of the radiation within the cavity. Okay. A laser radiation will continue as long as energy is applied to lasing medium, I mean as long as pump is there. Okay. So, this is the brief story about lasing. So, you see energy introduction, excited state, metastable state, I mean it is a non-radiation, by a non-radiation transition, non-radiative transition, metastable state is generated, then metastable state to the ground state. Okay. It is shown as a 3-level case, but it may be 4-level. Okay. So, then it is your stimulated emission of radiation. Okay. This is the schematic of lasing action. Laser output, like as I told in case of your helium neon laser or gas laser, it is as a continuous wave output. Okay. But for pulsed laser, it is I mean it is coming as a pulse, like energy, a packet of energy is given in a very short duration, here, maybe here, then here, and of course the gap between successive pulses is constant. Okay. So, it is a pulsed output, and that pulse output is possible by means of a mechanism that if you can rotate the 100% reflecting mirror at certain frequency, I mean rotational motion, then lasing action will be there only when the second mirror is exactly parallel to the partially reflecting mirror. So, like if it is like this, a little tilted, you won't get any lasing. So, this way it will continue to rotate, I mean like this. So, this is your mirror, it will continue to rotate like this. The moment it is exactly parallel, then lasing. When it is not parallel, it is not lasing. Okay. So, that this way you can get pulsed output. So, pulsed output is a means of is a means of getting bunch of a packet of energy, and the energy is packet of photons, and energy is huge compared to continuous wave case, and you can generate by means of this mechanical way or maybe other optical way. You can generate pulsed output. So, that I am not going to discuss in detail here, because it is outside the scope, and is the typical schematic of a ruby laser, that this is your active medium and this is your quartz flash lamp. Okay. And this one is 100% reflective mirror, and the other side is partially reflective mirror. I mean this side is partially reflective mirror, this side, and ruby lasing beam is here. Okay. It is discovered in 60s, and it is the power supply that is a source of energy that is supplied here. That is energy pumping is done by means of electrical energy is now converted to photonic energy by means of quartz flash tube. That flash tube excites ensemble from the ground state to the metastable, and then from metastable to the ground state, this transition generates your lasing. Okay. It is a aluminum monocrystal doped with chromium, it is called the ruby, and this is the schematic of the levels, that is these are the level, and lasing occurs over here, and its frequency is 694 nanometer. Okay. And optical pumping is done in this region, and lasing occurs in 694. Now, we will come to the actual discussion of this laser flash photolysis. It is the modified version of your just flash photolysis, that in this case, in place of flashlight, laser light is used. Okay. Laser source is used, light amplification by stimulated emission of radiation. So, here what is happening, that this is your sample where your molecules are there. Okay. This is xenon arc lamp that is used for your probe beam. It is a weak, it is not as intense as your laser. So, what is happening, that you have got your cell over here having molecules, xenon arc lamp, there is a filter that filters the unnecessary radiation, or maybe filter to select the frequencies for your probe beam. There is a shutter which maybe sometimes shuts off your radiation. This is your cell, then filter, because this is your probe beam. So, after the cell there is a filter to select the specific frequency, and then monochromator to further subdivide the frequencies, and then there is a detector called the photomultiplier. The signal from photomultiplier is given to the oscilloscope for digitization, okay, and then to PC. And here the excitation source means, I mean, the molecules are fast, they have to be excited, or maybe they will be given energy, so that further further reactions can take place. So, it is a 4-level Nd:YAG laser, okay. Then this 4-level Nd:YAG light is fed into a mirror, then another mirror, then to the cell that initiates the reaction. This mirror is is a partially transmitting and partially reflecting mirror at some specific angle. So, anyway, so this light is falling on the cell, it generates the excited ensemble of molecules, and then what happens that your xenon arc, the moment this laser is falling on your sample, a portion of your Nd:YAG laser light is fed into photodiode to turn on the oscilloscope. Turn on the oscilloscope means that time the oscilloscope will accept the signal from your photomultiplier, because photomultiplier is already on, okay. The moment laser light falls on, a portion of that light is triggering the photodiode to trigger the oscilloscope, so that oscilloscope gets the signal, and then this signal is fed to the PC for generating a decay pattern like this. This is the decay pattern. This is your OD, optical density, as a function of time, okay. So, this will, and analyzing this decay profile, I mean, will get us the time constants and decay factors, okay. So, in a typical example, this is your other case, this is another simplified description, that this is your xenon arc lamp, this is your detector, and this is your reaction vessel. It may be heated or it may not be heated, and this is your laser light, so that they are in perpendicular geometry, that is your probe beam and the laser beam is perpendicular geometry. In some cases, because you see there is a little interaction area, that a little portion of your active photo excited molecules are detected by your xenon arc this beam. So, that is why nowadays it is a perpendicular geometry. This is your laser this way, and this way is your probe beam. But other geometries are possible, that maybe this is your probe beam, this is your sample, and this is your laser light, so that the interaction area is a little more, so that you can get better signal. So, depending on your need, whether the sample is absorbing or not, you can choose the geometry of interaction. Maybe for your laser plus photolysis, it may be a perpendicular geometry or maybe a almost collinear geometry. Okay. In some cases, maybe the angle can be further reduced also. Okay. So, what is happening that let us have a concrete example, that let us take benzophenone. It is a widely studied molecule. Okay. So, what happens that in a micellar medium, okay, if we solubilize this benzophenone in say CTAB micelle or maybe SDS micelle. So, it gets solubilized. So, micellized benzophenone. So, micellized benzophenone. Then if this micellized benzophenone is excited, okay, it is excited with say a laser source. I mean it is flash photolysis. I am talking about laser flash photolysis, LFP, and the frequency is say 355 nanometer of Nd:YAG. So, BP will go to BP star singlet, okay, singlet BP star excited. This is also singlet, is a ground one. Then it will go to BP triplet. Then this triplet benzophenone will abstract one hydrogen from micelle, producing benzophenone ketyl. What is that? Benzophenone ketyl is this. Benzophenone ketyl. Okay. So, benzophenone ketyl radical. So, it is like here one hydrogen, okay, one hydrogen and maybe like that. Okay. So, here or maybe like, I mean it is better to write in this way. So, this hydrogen may be here, dot over here. Okay. So, this way, so this dot over here, so that means okay. So, this so we can follow this ketyl one, okay, we can follow this ketyl one, like it has got a specific absorbance at say around 550, okay. So, around 550 nanometer it will absorb. So, if we monitor at monitoring wavelength is 550, that is if we put the monochromator, this monochromator, I mean at 550 nanometer and then take the signal, we will be getting you know this decay of the benzophenone ketyl. Okay. So, this way we can follow, you know, we can follow the reaction in the excited state, using this this technique which is called your flash photolysis technique, and this is possible only when when your excitation, I mean like Nd:YAG source or maybe your flashlight is there. If there is no flashlight, then the excited benzophenone will not be produced to do this ketyl one. Okay. So, therefore, it is very important, it is very important, and also one important point, this one dot is over here and the other dot is on the micelle side. Okay. And then what will happen with time, again this hydrogen is given back to the micelle. Maybe some cases if it does not undergo further reaction, this hydrogen will be given back to your micelle. So, benzophenone BP ketyl will produce BP plus your micelle. Okay. So, benzophenone ketyl and your micelle dot is called a radical pair. Okay, is called a radical pair. That is why this radical, and also this radical pair can undergo several reactions which are very interesting. And this radical pair will, since it is radical pair, so radical pair can have you know singlet state, singlet situation, or maybe triplet situation, depending on their spin arrangement. Okay. So, and in presence of some external magnetic field, you can expect, you know, a modulation of their spin state. Okay. So, it will be very interesting, you know, maybe in later part of our discussion, maybe in next lecture, we can talk about this you know behavior of this spin pair, I mean radical pair, as a function of time in presence of an external magnetic field. Okay. So, this will be interesting, and radical reactions are very interesting. Okay. Anyway, so I will talk about this radical pair mechanism maybe in the next lecture, but let us try to finish off this part. So, therefore, we get we do flash photolysis, laser flash photolysis, and you know study this fast reaction maybe which happens in microsecond or maybe in nanosecond time scale. Okay. And so, this is a typical photograph for, I mean description for a flash photolysis. So, with flash photolysis we can, you know, detect, and especially laser flash photolysis, when absorption is less, you do not have much signal, then if you use a high intensity light source like laser, okay, if you use a high intensity light source with laser, then you generate a finite or definitive population of your excited ensemble. Okay. And you know you can expect more signal. Okay. Therefore, flash photolysis can be a very useful, especially laser flash photolysis nowadays can be useful, and selection of you know excitation source, okay, or pump source is very important. So, you pump energy into the system and then do your study. So, selection of excitation source is very important. So, you excite your sample and then you do further reaction. So, excitation source in terms that here in case of benzophenone we have used 355, maybe in other case you can use 532 nanometer, okay, or maybe IR radiation, or maybe 266 nanometer. So, and nowadays we have got many choices for selection of your excitation source to initiate the reaction. So, therefore, flash photolysis and laser flash photolysis is a tremendously important tool for studying, you know, transients, their fate. Okay. So, with this we will conclude today. So, in the next lecture we will talk about this spin chemistry a little bit, give you an idea about what is going on with this radical pair case. I mean the spin chemistry can be, or spin dynamics, or magnetokinetics, it is also called the magnetokinetics, that can be followed, using a laser flash photolysis technique. So, we will discuss that in the next lecture. Till then, that is all for this lecture. Till then, have a nice time. Thank you.